In this next subsection, I want to talk about binary search trees. It's clearly one of my favorite data structures because it's so versatile and so ubiquitous in computer science. I think almost all programming libraries have a good implementation of it. I think Python might be the only exception I know of. Um, it's a very useful technique. It's useful in practice, has lots of applications, but it's also beautiful in the theory. And there's lots of interesting research questions that are still widely open around binary search trees. It's clearly a fascinating topic, so I'm happy to crack into it. Again, many of you will have seen this before, so I will focus a little bit. I'll give a very brief introduction to the basics, but then focus a little bit on the more advanced comments that I want to make that sometimes are lost in a crowded undergraduate data structures class. But before we come to this, I want to ask you a little question on the side. I haven't prepared this on slide, so let me just add that. Okay, you should be able to see it now. And we can leave this open. It's just, this will be about the terminology of things. And I want to make sure I'm not talking about things that make absolutely no sense at all to you. So what I mean by physical dictionary is a book. I don't even have one here. I left most of my books are in my office, locked up safely on campus without any way for me to access them. I do have some physical dictionaries. Maybe I have a Longman English dictionary somewhere downstairs. Not even sure about that. Maybe even that's on campus. Okay, so most people seem to have used these, and you still know what these look like. That's good because that's a typical metaphor that's used in this context. Yeah, let's continue with this one. So I want to see, many of you have said they've seen binary search trees before, but I want to see how well that's stuck. Is there a way to jump to the? I have to hide this briefly. I don't want to show the answer right now. I want to give you a little more time for this. I want to talk while you're voting. I want to talk about the symbol table, abstract data type. This has many names. It's called, well, symbol table, obviously, but it's also called a dictionary. That's why I asked this question. That's what this picture is from. A physical printed dictionary in the classical sense of explaining words in one language or translating it to another language. You have these entries that are usually in alphabetic order, right? And then you can look up what's the meaning of a word, and it's exactly that sense that a symbol table represents as well. Sometimes also called a map. That's the name for the interface in Java. An associative array is the same thing, just slightly different syntax. And a key value store is also essentially the same thing, maybe more from the perspective of a database. The operations of a symbol table, I take the terminology so that it's consistent with the book and videos of Sedgwick and Wayne. But this is also how it's called in Java. So we have an operation put, and it gets a key and a value, and it just puts this key value pair into the table, which means it assigns the value v to the key k. We can also get back the value by this get function. So you give it a key and then it returns you the value that was associated with this key earlier on, if there is one. And you can delete a key. Well, you can delete the key value pair associated with this key. And you can check whether a certain key is in the dictionary. All right, few other small things. You can check if it's empty. You can check the size. You can create an empty one. These are all easy to do and not so interesting, so I won't discuss these in detail. I want to stress that binary search trees or symbol tables in specific, here we're talking about the abstract data type, so I'm sorry, I should say the symbol table is really the most fundamental building block in computer science. There's so many parts in programming that are solved by this. And here, really every programming library has some symbol table. I don't know any used programming language that doesn't have a symbol table. Not all do it by binary search trees, but almost all do. And there's a good reason for that. Okay, let me briefly revisit the question here. So here you see that most of you get this right. That's exactly what a binary search tree is like. So I can move on with that a little faster than for the heaps, maybe. I want to comment a little bit on this name. Symbol tables look very much like mathematical functions, and in particular, the name map suggests this analogy much more. They're indeed similar. The key difference is that a mathematical function is a static object that never changes. If you change the mapping in a mathematical function, then it's not really the same function anymore. It's a different function. It's a fixed object. It's immutable. It's a value if you want. Whereas symbol tables, we think of them as a dynamic mapping. You can change this mapping over time, and you can explicitly remove and insert keys, right? That's the key distinction. Now let's look at a few very simple ideas for implementing a symbol table. And you've seen this kind of dichotomy before, so not too much detail. We can use an unordered linked list. That's great for put, at least if we just append it at the end. So you can just add a new key value pair at the end of the list, and that's it. But if you want to find a key again, there's nothing you can do but just scanning linearly through the entire linked list, and that's slow. So you can do this, but it's almost never useful. You could think if unordered is not good, maybe we can sort the linked list. Now I stress linked here, and I'll come back to it in a second. Well, if you sort a linked list, that's actually totally useless, because now get still is linear time because you can't access elements faster. And put, now you have to maintain this sorted order, so you have to walk through the list and find the right insertion spot. So it looks like ordering the dictionary is not at all useful here. That's a bit against our intuition. But of course, you will probably know this. This is not quite true. Sorting, keeping the dictionary sorted does help, but only if we have an array. Why does it help? Well, if we have an array, we can search with binary search. So a quick reminder how binary search works. Here's an array with numbers sorted ascendingly, and we try to find a nice number, 69. We start with L and R. That's the range of the array that we still have to look into. And initially, that's just the entire array. And we compute the middle between those two. Now there's a tie. It could have been either of the two, but to make the example interesting, let's suppose you always round down the middle towards the left. Now you at this step, you compare 63 with the element that you're looking for. And obviously 63 is smaller. That means all of the elements on the left here, they're also smaller. So I can ignore all these elements with a single comparison. And that's the magic of a sorted list. You can do a single comparison in the middle, and then you know for half of the list that the element's not there. That's pretty good. So we do this, and then the range that we still have to look at shrinks like this. We do the same thing again. We compute the middle. We compare the middle 80 with the element we're looking for. And obviously 80 is too big, so we can exclude all this part as well. And we're left with this smaller window. Now we do it one more time. Oh dear, now I jumped all the way back. Okay, bear with me for a second. Should make shorter chapters, I guess. Still heap. Okay, there we are. Jump, jump, jump. So we do it one more time, compute the middle between those three. 77, still too big. So we can exclude all these guys, well, and all the others, but they were already out of the game. And so we're left with the 69, I'm sorry. And so the last comparison is to compare these two elements, and then we found the element. That's binary search. I'm sure that you will have seen this before, but just in case, I wanted to remind you again. And the key insight in binary search is whenever we do one step, one comparison with this middle element, we cut the remaining list in half. Well, plus minus 1 because of the rounding, but let's not be too strict about this here. What you can show if you take all the rounding into account is there's an exact upper bound of binary logarithm of n rounded down, but plus 1 because sometimes you have a little bit of a round off, so you get in a slightly larger list. That's the number of comparisons in the worst case to find whether an element is in the list and return its position, or find that an element is not in the list and return the position where it should be if it was in the list. The key thing I want to stress that here again is you need random access. If you don't have an array, you're pretty much out of luck with binary search. You need to be able to jump into the middle to make this efficient comparison there. If you cannot do this, then binary search is no help. You can't implement it. And the sorted linked list that we discussed on the slide before doesn't provide this random access. Okay. Long introduction. Finally, it's time to introduce the stars of the show today, the binary search trees. And I like this way of motivating them. We've seen a sorted linked list is almost useless because it doesn't provide a way to access elements efficiently. But once we have the position where we are, we can very easily add a new element into the list. We just splice a new element into the linked chain. On the other side, a sorted array was great for searching in the static case. When the dictionary is fixed, it was great to find elements efficiently. We could use binary search. But if you wanted to insert an element at some point, well, it's an array, so you have to copy everything over and move the element in. And that's again slow. So binary search trees are really the solution to take the best of both worlds. A linked representation that allows inserting at any point in time, but at the same time allow the access of an array to jump into the middle. That's the essence of a binary search tree. Yeah, so I wonder if we should do this question here before we move on. I probably should have presented this along with this slide. So let's just do this for a second to see if binary search is clear enough for you guys, and then we can move on. So same game as we've just had it. Suppose we have an array of numbers, and it's just the numbers 10, 20, 30, 40, 50, 60, 70 to make life a little more convenient. And you're looking for key 25. What is the sequence of comparisons that the algorithm that I just sketched would do? And maybe it helps you if I show this algorithm again. Okay, I'll give you maybe one more minute. 20 people have voted, 23. Okay, 28. Getting closer. We had up to 36 in the previous questions, so maybe I'll practice a tiny little bit of patience. As I said before, this unit is really tough for me because I'm jumping back and forth between trying to recap everything that I think a computer scientist should know, but also not boring the hell out of those who've seen this before. Okay, 37 is pretty good. Let's show the results, and the vast majority get this right. That's exactly what happens. So we jump into the middle. The middle between in this list is exactly 40. There's no rounding happening, so that's there's no ambiguity in the question. So you compare 40 with 25. Obviously, that's too big, so you jump into the lower half. So that's just these three numbers that are in your list. The next comparison is with 20. That's too small, so the only remaining list is 30. But you need this last comparison as opposed to the last answer, because you have to check whether 25 is in the list or not. Now, you reduce this to a single element list, but you still have to do the check if that single element list contains the 25 or something else, like in this case. Good. Okay, thanks for voting. Hope that wasn't too boring. Good, so that was binary search.